So what I want to do in this lecture is look at how we can prove some things. Um, Sometimes combinatorially, by thinking about counting, and the next one we're going to do, we're also going to rely a little bit on the binomial theorem. So how can we show this? Right, n choose r is equal to n choose n minus r. All right, well, think about what the right-hand side is saying here. We have a collection of n objects, and we're going to choose r of them. Right, the left-hand side is the number of ways we can do that. Okay, but what's going on the other side? And that says n choose n minus r. Right, well, what is n minus r? Well, look at what I've got on my diagram here. Right, if we have r objects over here that we chose, how many are over here? Right, well, this must be n minus r. Okay, so if I'm choosing r objects to be in my collection, I am implicitly choosing n minus r objects to not be in my collection. Right? And it doesn't really matter which way you do this. Okay, you can think of this one of two ways. You can choose r objects to be in the collection. That is equivalent to choosing n minus r objects to not be in the collection. Because once you've made one choice, you've kind of automatically or implicitly made the other choice, right? So these two expressions here are counting the same number of things, right? They're counting the same collection of objects, which means they're equal to each other. So what I want to do here is I want to derive this formula. And I'm actually going to do this two different ways. I'm going to do a combinatorial proof that's based on thinking about counting methods. And I'm going to do another proof that's algebraic based on the binomial theorem. Okay, so first, what's this saying? Because it maybe it looks a little weird. The left side is saying n choose 0 plus n choose 1 plus n choose 2 plus up to n choose n. And the right hand is just 2 to the n. So it's saying the sum of all of these combinations is somehow, with all the factorials and stuff that are in that combination formula, that is somehow equal to that very simple exponential expression. Right? So how can we show that? Well, to do that combinatorially, I want you to look at this question that I have right here. How many subsets does a set with n elements have? Now, first thing I want you to notice about this is that I didn't specify the size of the subset. If I had said how many subsets with 3 elements does a set with n elements have, that'd just be n choose 3 and we'd be done. Right? But no, I'm talking about all subsets of any size. Okay, well, one way to look at this is just to look at them all individually. This is the number of size 0 subsets plus the number of size 1 subsets plus the number of size 2 subsets, and so on up to the number of size n subsets. Well, what are these things? Well, the first one is n choose 0. The second one is n choose 1. The second one is n choose 2, and so on up to n choose n. Right, but that expression, that is just the left-hand side here. This is the sum k equals 0 to n of n choose k. Okay, hold on to that. There's another way we could approach this. Right, and the key to this is remember, there is only one answer to this question for a given value of n. Right? So if I can answer this question using a different method, whatever I get has to be equal to this expression because there's only one answer. Okay, here's another way we can approach this. There are n elements in this set, right? So there's n elements. For every one of those n elements, I have to make a choice. Either it's in a given subset or it isn't. Right? So for every one of these elements here, I have two options, in or out, in or out, in or out, and so on, all the way down to the end. Well, the multiplication rule says the total number of ways I can make these choices is just the product of all of these expressions, of all of these twos. Well, if I multiply n twos together, the result is 2 to the n. So another answer to this question, how many subsets does a set with n elements have, is 2 to the n. But, like I said, because there is only one answer to this question, for a given n, these two expressions must be equal to each other. Right? And there's the counting method answer. Right? Relied on the multiplication rule and our definition of a combination. Right? A couple different things, and the addition rule to get the left-hand side. A bunch of different things came together there. Okay, so how could I do this a little more algebraically, you'll see, right, using the binomial theorem. So I've got two expressions here, right? I've got, remember, this is what I'm trying to show, and then down here below what I've got the binomial theorem for us to work with. Okay, so here's what I'm going to do. I'm going to take that formula for the binomial theorem, and I mean, this works for any real numbers, a and b, right? Well, 1 is a real number, right? So I'm going to put 1 in there for a and b and see what happens. Right? If I do that, this becomes 1 plus 1 to the n equals the sum k equals 0 to n choose k, 1 to the n minus k times 1 to the k. The left-hand side, 1 plus 1 is 2, so that's 2 to the n. Hey, look at that, right? That's up there on my formula. And what happens on the right side? Well, 1 to the n minus k is 1. 1 to the k is 1. That part just went away, right? All that's left is the sum k equals 0 to n of n choose k. And hey, that's the other, okay, I got to twist it around, right? I have it reversed, but that's okay, right? It's the same thing. That's the formula that I was looking to derive. So this is the end of our discussion of the binomial theorem and Pascal's triangle, right? We do have one more chapter to go, one more series of lectures in our discussion of introductory combinatorics. We're going to talk about something called the pigeonhole principle. This is one of those things where when you look at it at first glance, it's maybe a little obvious, right? But you'll see as we get a little deeper into it, it is a very effective tool to have in our toolbox because it's going to let us derive and prove some other very interesting results.